Morning, respected Chair and Co-Chair, and dear audiences. Good day to you all. I am MS Balakrishnan, doing my research at Satyavarma University, and I am also working at the Government of India in the Ministry of Labour and Employment, where we develop skill for the industrial requirements at the low level, like welding, carpentry, electrical wiring, etc. And I, in that Central Training Institute, we teach the instructors who are working in the technical schools. And with that, we go to the research work that I have been doing under Satyavarma University. It's under power electronics, where we talk about the power converters. Now, the basic power converters, to just give you an introduction about the area of research work. We have converters which can convert from AC to DC, AC to AC, and DC to DC. And the more important of this is the AC output converters which generate from the DC. The DC input source and output as AC. Now, these converters provide a variable voltage output and a variable frequency output, and this variable frequency drives, especially applicable for speed control of the AC motor, they follow a V by F, that is voltage by frequency constraint. There is a limitation. The V by F should be constant in the complete process of controlling the speed. The formats available from these converters, they provide the standard sine wave output. You can have a variable amplitude, you can have a variable frequency, or both amplitude and frequency can be variable. The methodology used for generation of this sine wave output is the pulse width modulation control technique, where the width of each pulse that is driving the power switches is changed. Now we have a set of modulation techniques. So the modulation here is the pulse width is changed. And the complete algorithm is software controlled. The hardware uses a H-bridge, a standard circuit where DC input is given and you take a AC output. And the circuits again with motors, you have a single phase motor, three phase motors running with various capacitor connections and all those things. And now the latest technology research work is going on at multi-level inverter topologies. The application which I am referring to here is the AC motor drive with voltage by frequency control constraint for speed control of AC motor. The principle which I am presenting here is a comparison with a raised sine wave compared with the normal sine wave. What we get power here is a normal sine wave which is applied to the motor for running the motor. But what I am trying to present here is a raised sine wave that is firing the sine wave. So this is the normal sine wave that we get for all our electrical applications from the AC generators. Now what I am proposing here is the raised sine wave. Now this is a squaring. So when you square the sine wave, the negative component will become positive, but again in my formula, because it's a software control and the H-bridge, you can have the switches changed over. So it's possible to have a positive half cycle with two switches and a negative half cycle by changing the switch and changing the direction of current. So current flow direction is controlled by the topology. That's a hardware switch I will be showing that. But the wave shape, what I'm proposing here is the square. Now the reference of a sine wave is peak is 1. So all the values between 0 to 1, if you square, 0.1 square will become 0.01. 0.2 square will become 0.04. So the lower end will fall down. The 0.9 will become 0.81, where the difference is very less. So that is the advantage which I am trying to use in the design of an inverter. So you can see here, the area where the voltage crosses the 0, the amplitudes are less as compared to the normal sine. And in addition to that, these are the advantages that the zero crossing of the raised sine wave is very smooth near the crossing of the 0. The raised sine wave has peak rate of rise. The peak rate of rise is available here, not here. Whereas if you see the standard sine wave, the standard sine wave rate of rise will be maximum at 0. Now that's what you can see in the differential, the cos theta. So cos theta is 1 at 0. When omega angle is 0, cos theta is 1. So that is the point where the rate of rise is maximum. And it becomes 0 at the peak. Now cos theta governs the current flow in the inductive load, the motor being inductive load. The current flow will be maximum whenever the voltage is crossing the zero, and current flow is minimum whenever the voltage is at the peak. Now this is basically the problem when you do a power electronics design with the power switches like IGBTs and MOSFETs, and they are likely to fail because of the high current flow at the time of zero crossing on the voltage waveform. Now with this proposed method, the zero crossing area, because of the raised shape of the sine wave, the current flow is zero at that point. Now then where does the peak occur? So this is similar to the 2 theta waveform. So the peak will be here and here. That's the 45 degrees and 135 degrees. So the peak values are shifted away from the zero crossing of the voltage, and the fundamental frequency remains the same. So if you design for 50 Hertz, the output is still 50 Hertz, if it's 45, it will be still 45. So there is no change in the frequency, only the wave shape is changed. And that's what the differential I've explained to you, that the differential, there's a cos theta component which governs the current flow in the inductive load, has been shifted away from the zero crossing of the voltage for the modulation. This is a standard bridge for converting the DC into AC. Whenever switch S1 and S4 is closed, current flow will be through the load in one direction. Changing the switches to S3 and S2, current flow will be in the opposite direction. So getting the negative half cycle is not on the shape, because when you talk about racing or squaring the sine wave, all negative components will become positive. But here it is possible to get the negatives because of the switching. So S1, S4 will allow the current in one direction in the load, whereas S3 and S2 will allow the current in the opposite direction. So current reversal or AC voltage generation is possible because of the switching conditions. So one half cycle, S1 and S4 are switched, and the next half cycle, S3 and S2 are switched. The pulse width that is applied to these switches for generating the wave shape, sine wave shape. So in the conventional sine wave, we can see the pulse width. At the initial stage, the width is very small to generate the low voltage, and at the peak here, the pulse width is maximum to generate the peak output voltage. And this variation is according to the sine wave, that's the modulating signal. In the proposed raised sine wave, this initial peaks, you can compare these two, are width is less till about 10 degrees. And the peak in the center is same. So there is no difference in the peak value that you attain. Only the zero crossing area, the width is slightly reduced by using the raised sine wave as a modulating signal. And the generation methodology which I have proposed here, using a digital PWM technique, which is a software control. We can have a microprocessor or microcontroller based system. And these systems, for a 50 Hertz, the calculations are given here. And based on these calculations, the on time and off time of each sample is calculated, and this calculated on time and off time are stored in the memory, and each value is taken for each pulse, and the output pulse is generated by the output port of the microcontrollers. A brief idea of the algorithm that has been used, and here is where the delay subroutine. The delay subroutine is used to wait for the on time and off time for generating the pulse output from the microcontroller. A simulation was done with the MATLAB being a versatile software for controlling for engineers. And this is a simulation generated with the MATLAB. And in this one, the sine wave generators, the block used for generating the sine wave, has been modified to generate the raised sine wave. That means one sine wave is multiplied with another sine wave where only the absolute value is taken. That means the sign, the positive and negative, the minus and plus, so taking the absolute value, multiplying with the normal sine wave is giving you the raised sine wave output, and that is the modification in the complete design of the fundamental inverters. So the results which I have obtained here, with the conventional sine wave, the starting current is very high, whereas in the raised sine wave here, the starting current has considerably come down. So there is a nearly 18 to 20% reduction in the starting current flow in the induction motor. Similarly, the torque that has been developed, so the torque is also slightly less, but the starting torque is more going into making the armature to rotate from a stationary condition than pulling the load. So having a reduced torque at that stage is not going to affect your loading conditions because the armature is already stationary. So it's not actually pulling any load. So this actually reduces the losses at the starting stage. And similarly, the power consumed during the starting compared to the conventional sine wave, the raised sine wave has got 20% less power consumption. So that will be an added advantage because of the design. You will be saving energy, and motors that require frequent starting and stopping like lift, conveyor belts, elevators, wherever it's required to start and stop frequently, you will save a lot of energy by reducing the starting current parameters. So the advantages, the design and the complete method of using the raised sine wave for the design of the inverter is this effective. These are my references, which are taken from IEEE textbooks and various chapters. I invite the audience for questions.
I can see some advantages there, but there must be a disadvantage somewhere. What is the disadvantage?
Limitation. Limitation.
Imitation.
Is there, like your method has less peak power, less peak current, however, those are the advantages. There must be some disadvantage somewhere.
A disadvantage, as I told you, the torque value is less. But normally we call, whenever the torque is less, the power to pull the load has become less. That is where one thing which I have to test in hardware. I have to make, our hardware is almost ready. I have to perform some tests there. So the disadvantage, what the graph shows, that the initial torque has come down. But what I attribute is that the initial torque, the armature is stationary. So the current is flowing not for pulling the load, but for pulling the stationary armature. So there, I feel it's already a waste because the armature from stationary condition you have to make it to the full speed. So that is the reason for that one. And since we are reducing that torque there, one disadvantage that we may come is the load conditions. So under loaded conditions, I have to see what happens. So that I can, the results will be coming out when I do the complete hardware setup. And that is one disadvantage I expect out of this method.
In cost?
Cost-wise, it's almost same because nowadays with the variable speed drives, we are using power switches. The same control topology and same PWM technique is used. So the hardware part and the software part is almost same. Only modification is in the modulation voltage, the reference signal. So that's the only change. So hardware-wise, there is no change. In fact, because of the reduced currents, the reliability of the switches is improved. The failure rate of the IGBTs, the MOSFETs, the power switches should come down. They should not, because the current, whenever the sine wave is changing from positive side to negative side, the current is minimum during that time. That's where the switches operation change. So since the current is less during that time, the failure rate in the switches should come down. So the maintenance part should be now easier.
Maybe one more question for Mr. Wan. Okay, so thank you, Mr. Wan. That's been done.